So very good morning all of you. So in the last class I have explained about the impact diode. Okay, so its construction and its working principle, advantages, disadvantages and applications has been studied in the previous class. Okay, and in this class we are going to study about the TRAPATT diode. It is also one of the microwave semiconductor diode. Okay, and it is concerned to the subject advanced communication of the diploma ENC. It is fifth semester. Okay, so in this class 6, okay, in this so that we are going to study about the definition of the TRAPATT diode, its construction, its working of the TRAPATT diode, its efficiency, advantages, okay, its disadvantages and the applications. Okay, all that we are going to see in this class here. Okay, so if you take the definition, or if you take the full form of the TRAPATT, so the full form of the TRAPATT diode is, it is a trapped plasma avalanche transit diode. So in case of the impact diode, it is an impact ionization, it is avalanche transit time. But in this case, it is what the actual meaning of the first three letters, it is it is TRA, is going to stand as the trapped, and what the P indicating the plasma, A indicating the avalanche, and what the first T indicating the triggered, and what the second T indicating the transient. Okay, this is the full form of the TRAPATT. Okay, so if you take the TRAPATT diode, it is named as, it is a trapped, it is plasma avalanche triggered transit diode. Okay, it is also one type of the microwave generator. Okay, it is once again same as that of the impact diode. It is also one type of the microwave generator. It is going to operate between the hundreds of the megahertz to hundreds of the gigahertz. In the same way, so as that impact diode is going to operate from, it is 3 gigahertz to up to hundreds of the gigahertz, and also the more also. But in this TRAPATT diode, it is going to be get operated from hundreds of the megahertz to hundreds of the gigahertz here. And it is to be manufactured either from the silicon or from the gallium arsenide, GaAs, and it is implemented with the P plus N plus, or it is N plus P plus configuration. Okay, it is once again same as that of the impact diode. It's only difference in the width, okay, of the each layer. And what this TRAPATT diodes, the doping level between the junction and the anode changes gradually. Okay, so if you see the construction, or if you see the working principle, so automatically you are automatically will come to know about its variation in the junction and the anode. Okay, so I am going to repeat again. So what the full form of the TRAPATT is, it is a trapped plasma avalanche triggered transit diode, and it is also the one of the microwave generator. It is the microwave generator semiconductor device. It is going to be get operated from the hundreds of the megahertz to, it is hundreds of the gigahertz here. Okay, and what these diodes are manufactured either from the SI or from GaAs, and it is having the P plus N plus, or the it is N plus, it is PP plus configuration. And in this, what this doping level, okay, it is between the junction and the anode is going to change gradually here. This is about the introduction about the TRAPATT diode. If you see the construction of the TRAPATT diode, okay, so that you can able to see its construction, so that I took an example construction for, it is P plus N, okay, N plus configuration, so that you can see it is implemented from, it is P plus N plus, or N plus P, it is P plus. I took this example, okay, in order to explain its construction. Okay, so it is constructed either with the P plus N plus, or N plus P plus combination. In the diagram you can see it is implemented with the p plus n plus, and in this case what this p plus, it is approximately 2.5 to it is 7.5 micrometer, okay, width. And if you take the what this n reason, it is 2.5 to it is 12.5 micrometer. This is acting as the depletion layer, and it is the layer, it is going to enter into the plasma state, okay. And it is to be followed by the what n plus reason, it is approximately it is 2 micrometer here, okay. And if you take the length of this one, or if you take the height of this one, it is approximately 50 micrometer. It is for the continuous wave, and it is for up to the 750 micrometer if it is operating for the low frequency, okay. This is all about the construction of the TRAPATT diode, okay. Again I am going to repeat here, in order to construct the TRAPATT diode, it is implemented with the, it is p plus n plus configuration, or n plus p, it is p plus it is p plus combination, okay. So the example for the constructions so has been considered, it is for it is p plus n, okay, n plus configuration, okay. If you take the width of the p plus, it is approximately, it is 2.5 to it is 7.5 micrometer. It is to be followed by the n region. This is nothing but the depletion layer. It is the layer enter into the this plasma state, and its approximate variation is from it is 2.5 to it is 12.5 micrometer range. And it is to be followed by the one more layer, it is the what n plus layer, and it is approximately of the 2 micrometer here. And if you take the height of this one, okay, it is approximately 20 it is approximately 50 micrometer if it is going to be operated for the continuous waves, and it is going to be the 750 micrometer if it is going to be get operated for the low frequency and the high peak power. If amplitude is high and if the frequency is low, it is going to be approximately 750 micrometer height here, okay. This is all about the arrangement, or it is all about the constructions of the TRAPATT diode. If you take the working principle of the TRAPATT diode here, so a TRAPATT diode in operation is placed in the high resonant cavity, and it is black bias to the avalanche threshold. Obviously it is going to be get operated under the reverse bias, okay. And it is when the RF oscillations begin, okay, they build up extremely, it is rapidly due to the resonant structure. It is thus taking the voltage across the diode to a value it is much above the avalanche threshold, okay. So that initially it is going to be get applied with the DC voltage, and after application of the RF oscillations, RF means it's the radio frequency signal, it is to be get overlapped with the DC voltage, and afterwards it will cross the avalanche threshold here, so that the voltage is going to across the diode to a value that is much above the avalanche threshold. It is going to enter into the negative resistance here. And what is electrons and the holes is going to be trapped in the low field region is behind the zone, are filled or made to fill the depletion region in the diode. This is done by the high field avalanche region, it is which propagates through the diode here. That means that you can see in the diagram, yeah, okay. If the recombination of the DC and the AC is going to take place, the increasing in the velocity of the electrons and the holes takes place. It is going to be get multiply with the electrons and the holes in this region here. You can able to see the depletion region. In this region, it is going to be get traveled. It is towards the what anode or cathode here, according to the arrangement here. So for that purpose, the electrons and the holes is going to be trapped in the low field region. It is behind the zone and are made to fill the depletion region. So what this depletion region is going to be completely filled here, okay. And after that what happens here, okay, it is to be what the high field avalanche region which propagates through the diode. After the recombination, it is going to be filled here, and after filling, it will travel towards the other end of the diode here. Okay, and after that, what this transit time calculated here is the time between the injection and collection. So that is how much amount of the time it is going to generate the output after giving the input here. Injection is nothing but applying the RF signal, and what this collection is nothing but the output is extracting from the other end here. So how much of the time it is going to take in order to move from the one end of the diode to the other end of the diode here. So how much amount of the time it is going to take? So it is itself is called as of the transit time. It is to be calculated based on the injection and the collection. So at what time the input has been applied and at what time the output so has been taken. If the output time it is minus the input time, means it is going to give you the transit time here. Okay, so what this repeated action increases the output to make it as an amplifier. So if it is going to be repeated continuously, it is going to increase the recombination of the electrons and the holes in the depletion region, and it is itself is acting as an amplifier here. And if you make use of the one, it is low pass filter, okay, along with this diode, it is acting as an oscillator here. Okay, this is, it's very simple. Okay, I am going to repeat it once again. So a TRAPATT in operation is placed in the what? High resonant cavity. So it is under the black biased, under the back, it is reverse biased condition. And after applying the RF oscillations, it began extremely rapid in the resonance structure, and the voltage is going to cross above the, it is avalanche threshold. And what this electrons and the holes is going to be trapped in the depletion region, that is in the middle region. And what this middle region, it is going to be completely filled here. After filling, it will try to move it, it is propagated through the diode here. And what this transit time is calculated here is the time between the injection and the collection here. At what time it is injected, at what time the output is taken, and if you take the difference of that one, it is going to give you the transit time. And if this repeated action increases, it itself is going to act as an amplifier. And along with this diode, if you make use of the low pass filter, okay, it is which is connected exactly parallel to that one, it is going to work as an oscillator here. Okay, so that it's working, it can also be explained with the, it is with the help of the graph here. So this is the graph of the voltage and current, it is with respect to the time here. Okay, what this part is for the half cycle, and it is what this another part is for the another half cycle here. Okay, so initially the AB shows the charging. So initially the voltage is assumed to be the sufficient. Okay, at the voltage is going to be the sufficient. What this one? So it is acting as of the one end, and it is acting as of the one. It is other end, and it is what this depletion layer. It is acting as of the dielectric, and so it is acting as the capacitor. And if it is acting as the capacitor, on applying the some amount of the voltage, it is going to be get into the charging. It is going to increase the number of the electrons and the holes in the depletion layer. That means that it is going to keep on charging. If it is going to keep on charging, means so the voltage, it will increases from A to B. So in the A to B, it shows as the charging. And if once the depletion layer is completely filled, it will try to discharge. So if this depletion layer is completely filled, it will enter into the plasma state. enter into the plasma statement, it will try to propagate. It will try to propagate. If it is going to try to propagate means it will act as the discharging. So the BC it is going to shows the plasma formation. So the voltage is going to be discharging immediately, extremely. I said that it is while explaining. Okay, it is extremely rapid here. So extremely rapid, it is going to start discharging here. And after that, what this D shows the plasma extraction. So what this plasma, it is going to be continued up to the D, and if it attains the minimum, so it will try into the extraction now. So it will keep on, it is slightly increasing, so it is going to recovering from the plasma state. And what this EF, it is going to act as of the residual extraction. So that again it is going to try to form as the capacitor, and the voltage will keep on increases. It is slightly. So all the electrons and the holes available in the depletion layer is completely propagated. And what this the depletion layer, it will become empty, and it will again starts, it is what it is enter into increasing the, it is recombination of the electrons and the holes. It will enter into charging again. So what this Fg shows the charging. And again when it attains the point G, so what this diode current, it comes to the zero for half a period. So that half cycle has been completed now. And for another half cycle, it is going to retain its position until the next cycle is going to be get started. And again it will increase from A to B. Again this cycle is going to be repeated, and again this cycle is going to be repeated. In this way the working takes place. Okay, so it's very simple and it is very easy to remember also initially. So the what that DC voltage is to be get, it is superimposed on the RF voltage, and it is going to act as the plasma, and the voltage is going to cross above the avalanche, and after that it will enter into the recombination of the electrons and the holes in the depletion region. And after that it will enter into the plasma state, and it will keep on discharging the electrons and the holes. And after completely discharging, again it will start into, it is charging, it will enter into the maximum peak, and again the cycle will be repeated here. So the A B point is called as the charging. What this the BC is the plasma formation, and what this CD up to E is the plasma extraction state, and what this E to F is the residual extraction, and what this F to G is again the charging. And at G it is going to remain the constant until the other half cycle will come to zero. It is for the zero for half a period, and again the cycle is going to be repeated here. This is about the working of the TRAPATT diode. Okay, and the next, if you see the equation, so the avalanche zone velocity, it is Vs is represented by Vs is equal to, it is a differentiation, it is dx by dt, which is to be indicated as of J divided by this Q into Na. It is where J is the current density, J is the it is current density. What is Q is the electron charge, and I think you know that what is the value of the electron charge. It is equal to 1.6 into, it is 10 to the power of, it is minus 19. The Na is the doping concentration. It is indicating the width, or it is indicating so how much amount of the dopant has been added to the original tetravalent element, either the silicon or GaAs. Okay, and the avalanche zone is, it is going to quickly sweep across the most of the diode obviously. And if you take the transit time of the carriers, is to be represented as of the tau s is equal to L divided by Vs. It is where the Vs is the saturated indication of the S is the saturated. It is carrier drift voltage, and what this L is the length of the specimen. What this length of the specimen in this case means, this is the depletion layer length. Depletion layer, okay, length. This is indicating used to calculate the transit time here. Understood? So the avalanche zone velocity, that Vs is equal to, it is equal to J divided by Q into Na. J is the current density, this Q is the electron charge, Na is the doping concentration. And if you take the transit time, it is to be given by it is L divided by Vs. It is where the Vs is the saturated carrier, is drift velocity, L is the length of the specimen. Okay. And if you take the advantages of the TRAPATT diode, it is going to consume the low power. It is low power dissipation. But in case of the impact diode, so I think you have seen it is of the high power dissipation. But in this case, this is of the low power dissipation. And the efficiency is what higher. It is up to the 60% here. And if you take the TRAPATT is a pulse capable of operating at much larger pulse powers. I think you have observed in the diagram or not, it is inputted the DC with the square wave current, square wave. But in case of the impact diode, the voltage applied is of the very high. It is equal to, it is 400 kilowatt per centimeter has been applied in case of the impact diode. But in this diode, it is going to be get operated with a single pulse. Okay, so it is advantages. It is of the low power dissipation. The efficiency is high up to 60%, and what it is going to make use of a pulse device capable of operating at much, it is larger pulse powers here. If you take the disadvantages, so the high noise figure 60 dB, it is going to limit its use as an amplifier. Okay, it is going to limit the amplification factor up to the 60 dB. And if it is exceeded above the 60 dB means along with the signal, it is also going to amplify the noise also here. So high noise figure if it crosses the 60 dB in an amplification. It generates the strong harmonics. It is due to the short duration of the current pulse. I said that it is to be get activated by a single pulse here. So it is of the very short duration here. If it is of the short duration means it may treat it as an harmonics also. So it generates a strong harmonics. It is due to the short duration of the pulse, and the operating frequency is limited. It is below the 10 gigahertz. So hundreds of the megahertz up to it is 10, okay, gigahertz is to be its operating. And if it's exceeded above the 10 gigahertz means it is going to induce the noise there. Okay, all these are the advantages and disadvantages of the TRAPATT diode. Okay, and if you take the applications of the impact diode, it is used in the low power Doppler radar. It is used in the local oscillators for the radar. It is used as of the microwave. It is beyond it is landing system. Used in the radio altimeter. Used in the phased array, okay, radar. So almost all it is mainly used in the radar system here. Okay, what the radar, what this meaning of the radar, what actually it's working. So that is there in the unit 2. Okay, now only thing is to remember actually the uses of the TRAPATT. I'm sorry, so it has been misprinted here. It is impact. It's not the impact. It is TRAPATT diode. Okay, please correct it. Applications of the TRAPATT diode. It's not the impact diode. Okay, so that I'm going to correct it. It is mainly used for, it is low power Doppler radar, used in the local oscillators, used in the microwave BM of the landing system, used in the radio altimeter, used in the phased array radar, etc. So all these are the applications of the, it is TRAPATT diode. I'm sorry for this one. It is TRAPATT diode. Okay. So in this class, so I have explained about the introduction of the TRAPATT diode. Okay, it is the trapped, it is trapped plasma avalanche trigger transmit diode. It is acting as of the microwave semiconductor generator. It is going to be operated from hundreds of megahertz to gigahertz. It is implemented with the silicon or implemented with the gallium arsenide GaAs. It is implemented with the p plus n plus combination, or n plus p, it is p plus combination. And it is going to change its junction gradually. I think you have seen that it is going to form the plasma state, and afterwards it is going to reconstruct, and after that enters into the residual, and afterwards again charging. So it is going to change the junction there. And its construction, it is implemented with the p plus n plus, or it is n plus p plus configuration. And what is p plus configuration is approximately 2.5 to it is 75 micrometer, and if you take the depletion region, it is approximately 2.5 to this 12.5 micrometer. And if you take the one more, it is one more layer, it is approximately 2 micrometer. Okay, and if it is used for the continuous waves for the AC, it is going to its height is going to be approximately 50 micrometer. And if it is used for the low frequency of the, it is what high power, it is going to be up to 750, it is micrometer here, its construction here. If you take its working principle, it is going to be operated under the high resonant cavity. Okay, and after application of the radio frequency oscillations, it is going to build up extremely. And what this voltage is going to cross the avalanche threshold, and afterwards this electron sign, the holes is going to be trapped in the depletion region, and it is going to fill the depletion region. And after completely filled, it will try to propagate into the diode here. And after propagation time is calculated with the transit time. It is nothing but the difference between the, it is collection and the injection time and the collection time. And it is going to be repeated continuously in order to act it as an amplifier here. Okay, and if it is to be explained with the graphically, means what this AB is the charging, what this BC is the formation of the plasma, CD and up to DE is the extraction of the plasma, and what this EF is the residual extraction, and FG is again charging, and GA is going to maintain constant for the another half cycle here. Okay, and if you take its equation for the velocity indicated by, it is equal to g divided by qna, and for the transit time indicated as the ts is equal to, it is l divided by this vs. And advantages, it's of the low power dissipation, efficiency is high, and it is going to be get activated with a single short pulse here. If you take the disadvantages, it is increase the noise if it exceeds above the 60 dB, and it generates the strong harmonics. It is mainly because of the short duration pulses, and its operating frequency is limited up to 10 gigahertz. Okay, applications, it is used in the low power Doppler radars, it is used in the local oscillators for the radars, it is used in the microwave beyond for the landing system, it is used in the radio altimeter, it is used in the phased array, okay, radar, etc. All these are the applications. If you take the sample descriptive questions of this one, means, so he may ask you to define the TRAPATT diode, or he may ask you to explain the construction and working principle of the TRAPATT diode, or he may ask you to list out the advantages and disadvantages of the TRAPATT diode, or he may ask you to list out the applications of the TRAPATT diode. So all these are the possible questions of the today's topic covered. Okay. So in the next class, we are going to explain about the microwave tubes. It is what now, up to now, impact diode and the TRAPATT diode, or the microwave semiconductor devices. Okay, so you don't confuse. This what is impact diode and TRAPATT diode, or the microwave, this semiconductor, okay, devices. And in the next class, we are going to study about the microwave tubes. Tubes means it's the magnetron or the klystron, etc., etc. All will be there. So it will be studied in the next class here. Okay. Okay. Thank you. Okay. Thank you very much.